In this lecture, now we will see what is the plane wave propagating in general direction. Specifically, we have studied the plane waves, that is the uniform plane wave, in either in the along z direction or the x direction. Now we will see for the general direction and what are their expressions and what are their different parameters for this one, and especially the direction cosines. So to understand the plane waves propagating in general direction, let me use this whiteboard. So what we have, for example, a wave is propagating in z direction. So let this is the z direction, and these are the other two axes here. This will be the x, and this will be the y. So if, for example, we have the electric field that will vary along the z direction here at a particular time. And generally we give this expression by using the formula cos uh, omega t minus beta z. So here this beta z, let for this one, this beta z will give you the phase for a particular time. This beta z will give you the phase. How to find the phase? For example, this is your this one is a wave propagating in z direction. So for example, you are at this location, z equals to, let this z equals to here uh, 3 lambda by 2. If this is here, you have the 1 lambda, 3 lambda by 2. So to find this phase, what you do, you multiply beta with this value of z. If this is z, so multiply with the z will give you the, so beta is 2 pi over lambda, and you multiply this with the this value of z up to this point, this distance. You multiply this distance from origin to this point to get the total phase. So here we have taken the example z is 3 lambda by 2. So here comes out to be, and this will be cancelled out, and you have 3 pi, which is there. You can see that you have total phases now 3 5. Here it is 2 5 for 1 lambda, and it will be one more pi, and it will be 3 pi. So similarly, if you have another point z, for example, if you have take here, you have again take this z axis, and wave is propagating in this direction, and instead of having the value of only z, somebody give you the point on this space coordinate here. Because this is a uniform plane wave, so it will have wave front. For example, you have the wave front, which will be, this is the wave front. What is the wave front? Where all those points where have the same phase. Here. So for example, this is a point crossing this plane. So at this plane, all the points have the same phase. So if it is 0 here, they will be 0. So if this is the axis, then let's, this point is here, P you define. This is a point P, will given some comma x, comma y, comma z. So how to find the phase of this point in general? So we need to find this phase. This is a first we we have to find this distance from here to here, and then we multiply this distance with the beta. So here, if this distance, if for example d, you have to find d, and then you multiply uh, beta with d, then you will get the same phase. Or what you can say, this is the projection. If you take here, if you take this vector, you consider this line to be a vector here, and this is a vector, and this vector, because it's x y z, so we take vector to be r vector here. And if we take the projection of this vector along this z axis, then you will get that this distance d. So if this is az, if this is az component. So you take the projection of R over AZ, then you will get this distance D. So here in this case, this distance D will be given by just you take this position vector R, position vector of this point P, the projection over to the AZ, and you will get this distance, same distance D here. So this will be the just two. So any point you can take on this plane, and just you take the projection along this AZ direction, which is the direction of projection of wave. You will get this total distance, and then you multiply with the beta, you will get the total phase here. This is how you compute. So just taking this one. So what you have to do, you have to multiply. Then total phase will be just you multiply with this R, with the projection of R with the AZ, then you will get the total phase. How you get the total phase? Now this is a case when wave is propagating in the Z direction. Now if the wave is propagating in general direction, similar analysis you can do to find the total phase. So let me consider now the in general direction. So what you have, for example, you have again, let this is the, let this is X, uh, this is the Y axis, and you have this one is the X axis, and now this will be the Z axis. Okay, now wave is propagating in particular direction. So let's take that this wave is propagating in this direction here, and this direction is, we denote the unit vector AK. So now wave, the electric field vector is varying in this fashion here at a particular instant of time here. Now again the wavefront for this case will be, wavefront for this case will be, for example, here you have the wavefront. So let me rub this part. So you have the wavefront. So this is a point here. So again the wavefront for this part will be, this wave will be the plane perpendicular to this one. So here you have this axis is intersecting at this point. So this is the plane perpendicular to this direction, and they have the same phase, whatever the phase is there at this point. Okay, so again to find the total phase of this, because this wave is given by the total phase of here to here, it will be just you take another the point P is point, and whose position vector is given by R, and you take the projection of this over to this point, then you find that this distance D. So this distance D now will give you the, so what is this projection? So if you have this AK direction, so you take the projection of R over to this AK, then you will get that this distance D. So D distance now is same as you have R projection over, let's take the dot product, they will give the projection AK will give you this distance, and total phase will be just given by now beta into D, which is equals to beta times R dot AK, this one. Okay, so this is how you find the total phase. So this will be the same phase. So if you want to find this phase, so this distance, this will be the same as D, and you will find the from here to here total phase has changed by this much amount. Now next we can write this here, beta D, the total phase change is beta D equals to, now here you have, you can take inside, so you can write B times AK dot with R. You will get the same result what you are getting here in this case. Now we define this BAK as a new vector, because b is a phase constant, ak is the unit vector along the direction of wave propagation. So we define the new vector. This is k vector, wave number vector, which is equals to beta times ak. So therefore this will give you, this implies you that therefore now this phase beta d can be just, you can compute using k vector k dot r. So when you have the k dot r, you will get this projection and you will get the same phase. Now k, where k will give you, where beta can also be written, if you know the k vector, you can just, you can use the magnitude or k vector of magnitude. So if a k is given, wave number vector is given k, then just you take the magnitude of this, you will get the beta, that is the phase constant here. So this is how you define this one. So now the wave will look like the wave propagating in general direction, which will have, so let's take this one. So wave electric field somehow vector will be given how some here. So this vector will be somehow E naught, and now it will be some sort of cos omega t minus this phase k dot r. This is how, this is the wave. Here some direction is the AE, and this direction AE is perpendicular to the AK direction. This direction will be, so this is a wave which is moving in general direction along the AK, along the K direction. So here this wave number K, this wave number vector K will also give you the direction of propagation. So wave will propagate the direction along the this K vector. This is how you can come. This is a general expression of the wave moving in the K direction. Okay, K. Now, and this, the direction of the E vector E have, this direction will be perpendicular to this vector. The next, you can have this K. K can be computed as, now this K is a vector, so it will have a, you can decompose this into the unit vector, so it will be called Kx, and this will be Ax plus Ky, it will be Ay plus Kz, Az, and you know R is a vector which is a position vector. Once you given x, y, z, this will be Ax plus, you have the y, Ay, and plus z, Az. So this vector, therefore k dot r will be just as a kx x plus ky ay plus kz az. So in this case, now the equation of this E vector, so therefore E will be written as some sort of E naught cos omega t minus this, you have kx ax, and now you take the bracket here, kx plus ky ay plus kz az. Sorry, I have a mistake here. So this will be not the case. This will not the ax, but rather it will be here, it will be x, y, and z. Will be x, y, and z. So this is how now general equation look like. So where kx is the component of the k vector along ax direction. Similarly, ky is a component of this phase number vector, wave number vector along the y direction. Kz is the component along the z direction. So this is how this will look like. Uh, Second, this kx, uh, we know that beta generally we use. So see that as kx, you can also write this beta x. It will be beta x. Now we have a kx, and beta y is ky, and beta z equals to kz. Similarly, we can define the lambda x, which is now 2 pi over lambda, 2 pi over beta x, plus lambda y equals to 2 pi over beta y, and lambda z equals to 2 pi over the beta z. And just to find the lambda is just a 2 pi over beta, or 2 pi over this magnitude of this wave number factor. Okay, so how you understand the lambda x, lambda y, and lambda z? Let's draw the figure. So again, this is this is some, we focus on the two dimension to understand this one. Let this is uh, x direction and this is the y direction, and wave is propagating in the xy plane along this direction, some here ak. So if you the lead wave is propagating in this fashion. So how you define the lambda? Lambda is just difference between two peak, that is a two creased or two troughs. So let we define here. We have this line we can draw here. So if we focus on this, so this distance is called the, that you have two peaks. So here we have this lambda is defined here. So this is the lambda here from here to here. Okay, difference between two creased. Now simply if you move along the x-axis, so when you're moving this, so you will first encounter the peak at this point, and then you will feel the peak at this point, because it's a uniform plane wave, so everywhere they will be repeated. You have this plane. So if we draw the plane, this is the plane here. So this is the first plane where you will have all the same peaks will be there. Similarly, another plane where you have the all the peaks. So when you move from this plane to this plane along this AK, you will get the lambda. But when you move this plane not along the AK direction, but you move the AX direction along this parallel to this axis, so this distance will give you the lambda x here one. Similarly, when you move from here, for example, this point to this point in the same phase. So when you encounter in the y direction, that you have this plane, so this will give you the lambda y. The first peak will come here when you move in the y direction. Then there will be no peak until you get here at this point. You will feel the same peak. Means when you meet these two planes, when you move from this plane towards the y direction, and when you move the another plane which have the same peak, first peak repeated, the peak is repeated, that is called the lambda y. Similarly, when you move in the x direction, from this point in the x direction, and you find the next plane which have the same peak, then you will have the lambda x. So this is a lambda x, and this will be always be greater than this lambda. The lambda x, lambda y will be greater than the lambda. So you will see that lambda I The minimum distance between these two planes always the perpendicular distance between two planes. Another distance are not, these are not the perpendicular distance, these are not the perpendicular distance, so they will always be greater than the, so lambda x and lambda y will always be greater than lambda. Similarly, you can see on the z-axis, if you have the z-axis also, then what will have, so you will move in the z direction, so you will encounter the next plane, so you will lambda z. So this is how you feel the lambda, what is mean by the lambda x, lambda y, and lambda z. Okay, so this is how you can write. So this is what we have covered in the first part. So this is all is explained here. So how you can write this one. So lambda x and lambda z, you can go through this one and we can find this one. Now next is what are direction cosines? What are direction cosines and how we can write the equation in the direction cosines forms. So the next for we can, this is a general equation. This is the, here we have the general equation. This one, this is one equation, general equation, and another one was here, this one. So both are generally used to show the wave moving in the general direction. So this will represent, this part will represent the general direction. Okay. Now we can write this equation in terms of the direction cosine. So let's move to the what is mean by direction cosine. So so we have a wave again. We take some this x-axis. Let's take again, this is the y-axis and this is x-axis, and let this will be the z-axis. Now wave is propagating in this direction. This is the direction of k and we show with the unit direction ak. That will also have the k vector k1 here, wave number vector. So now this the wave propagating in ak direction has angle. So this is, let this angle from x-axis is we define as this one, the angle we define as theta x, and this angle uh, for here to here, from this angle from y-axis, the x-axis is theta x, from y-axis this angle is theta y, and we can have another this one. So let's take some other one. So in this case, so this one will be the, this will be the theta z. So these are the angles which are made by this this direction ak with x-axis, y-axis, and z-axis. Now next we want to break this ak in terms of unit vector. So we have this ak vector. So we have this vector ak, and we want to find we want to decompose this vector in terms of the unit vectors along x, y, and z. So along y will be this vector, and here this vector. So here will be this vector here, and we want to find. So we want to find these vectors when we decompose. So it will give you these vectors here. So how to find this one? This we want to. This is y, this is x, and this is z axis. So we want to find the unit this ak vector. We can decompose any vector in terms of their unit vector. So how to find this component vector? So this component vector here, this component vector here will be just, if you take the projection of ak along this AY axis, then this will be the projection component, and you multiply with the unit vector, you will get the the vector component along this y-axis. So this will be give you, you take AK vector and you project along AY. So this will give you the scalar component, this distance you will get, and then when you multiply this the AY, so this will give you the vector component. Now what is AK dot AY? So if you know this angle is theta y, so you can open this magnitude of AK, magnitude of AY, and the angle between this will be the cos of this angle. So here finally it will what you will get, this will be the cos theta y into AY vector. So this will be just a theta y because magnitude of AK and AY is 1. So it will be only remain the cos theta y. So this is the vector component along this direction. Similarly, you can decompose AK into X and Y. So same thing will be there. So what you can write now, the AK vector will be equals to cos theta X, and this will be AX, plus cos theta Y AY, plus cos theta Z AZ. So this is, you can decompose the AK vector in terms of the AX, AY, and AZ using this angles. If you know these angles, these are called the direction cosines. This part is called the direction cosines. So cos theta X, similarly cos theta Y, and cos theta Z are called the direction cosines. Direction cosines. Okay. So this is how you, so if you know these angles, you can find this unit vector by using this method. This is very important. So this is how you find the unit vector. Once you find the unit vector, you can find the you can just find the k wave number. So going through this again further. Now what is k? K is given by, you have k vector is just n k times ak, and using this one, what you have, k will be here, you can replace, so you have cos theta x ax plus cos theta y ay plus cos theta z az. This is how you can compute. So this will be k times cos theta x ax plus k cos theta y ay plus k cos theta z az. This is, you have the k vector. Now if you compare this one with the previous k, what we have written, so previously k was written as, so k was written as kx ax plus ky ay plus kz az. So from comparing these two equations, what do you see that kx is equals to k cos theta, and ky equals to k cos theta y, and kz equals to k cos theta z. So if you know the k or beta and you know the direction cosines, you can find the component of k along ax, ay, and az. So this is how you can write. Similarly, then you can find the lambda x. So lambda x you can just go on will be the 2 pi over x, 2 pi over kx, and just it will be equals to 2 pi over beta cos theta x. Similarly, you can find the other one. So now the equation will be given by in terms of this direction cosines. So these will be given by E naught, E naught, and here it will be cos omega t minus. So what we earlier we have the kx ax. So now it will be just a k times or k times what do you have cos theta x x plus cos theta y y plus cos theta z z, and this will be how you can write this one, and then multiply with the AE direction. So here you can write this equation in this form. So this is the equation of electric field, a wave moving in a general along the k direction. Now here k is a magnitude, not the vector. Or you can instead of here you can write the beta also. So this you can remove and you can write the uh, beta here. That will be beta. So this is the equation of the wave of the electric field moving in the k direction, ak direction or the k direction, same thing in terms of direction cosines. So this is how this is a E vector. Uh, so these things are explained in the note. You can go through this one. So direction cosines we have explained here. Uh, these are the direction cosines, and you have this equation cos x cos theta y z. So you can either write k before or omega t minus, you will have the same results. So also here I've also explained some other things in general. So you can go through one by one quickly. So these are different method I have used to explain, and right now I have explained the different approach. The two are the different approach, but you will lead to the same thing. So here what you have k, this you are getting the k dot r general equation, and for either a two dimensional we have taken, and you are getting the same equations. Now here you can find the angle. If you have the this one kx upon ky will give you the this angle. Either the two dimensional. So but rather we have to focus on three dimension. So no need to remember all those things. So now the phase velocity can be obtained just by using omega over beta, and here the magnitude of beta you can find just kx square plus ky. So for in general the magnitude this v will be given by omega over kx square plus ky square plus kz square. This is how you can find the uh, phase velocity in this one direction. And similarly, you can also find the phase velocity along the ax and az. So this is just vpx over omega over kx, vpz over omega over kz. And these phase velocity will be because this kx will be uh, I think it is you can see because lambda x is larger, so this omega over lambda will be smaller. No, no, no. This is correct. Vpx and Vpz is greater than Vp phase velocity here. Okay, we'll see it later. However, the wave frequency omega over this omega over 2 pi is invariant. It will remain same. So you have omega over 2 pi is the frequency. The frequency will remain same. So here three dimension you can have these equation lambda x over 2 pi over kx, lambda y This is correct because this is not the lambda x, this is the kx. So lambda x will be smaller. So lambda x will be larger, so kx will be smaller. So omega over kx will be larger. When you write this will be vpx. So vpx equals to omega over 2 pi into lambda x. So lambda x is larger. So omega this VPX will also be larger. So lambda x more than lambda. So VPX will be more than the VP. So so VPX will be more than the VP. Similarly, the phase velocity along the y component will be more than the phase velocity VP. So you can go through this one. So here you have an example. Consider 50 megahertz uniform plane wave having electric field up to 10 volt per meter, medium and lossless having the this one. The wave propagates in the xy plane at a 30-degree angle to the x-axis and is linearly polarized along that. Write down the phase expression and so on. So you can go through this one and you can find the so kx will be the k into cos theta. This because two dimension. So this angle is the theta x and this theta y. So theta y is this one 90 minus 30. So it will be the you can find this one. So you can find kx ky. You can find then k is this one, and you can go through es the phasor form k dot r dot. Then you can go. This is the equation of the e because E is the linearly polarized along z axis, so it will be the electric field direction is the z axis. So you can go so you can go through these nodes, and here we have a different approach, and what I've explained is a different approach, and you can understand the both way. Okay, so now we in the next one we will see so reflection and refraction when the waves are incident at an oblique angle to the interface of the two mediums. Okay, I stop it here.